Hello, welcome to MathsMastery with Benjamin, where we make math simple and fun. Today we're diving into an interesting topic, sets and operations and sets. Grab your notes, stay focused, and let's master this together. Don't forget to like, comment, and subscribe to my channel for more Maths Mastery. And be sure to ring the notification bell so that whenever I drop a new video, you'll be the first to know. Now let's get started. So we begin with the definition of a set. What is a set? So a set is any collection of well-defined and distinct elements or objects. So these elements or objects we're talking about here can be numbers, letters, people, or any items of interest. Sets are normally denoted by capital letters such as A, B, or C. So depending on the set given. And its elements are enclosed in a curly bracket. So this is a curly bracket. So for example, set A contains 1, 2, 3, and 4. So 1, 2, 3, and 4 are the elements of set A. So these are the elements, and this is the set A here. Now let's get straight into the methods of describing a set. Now the methods of describing a set. So there are three main methods of describing a set, and I'm going to take you through one after the other. And these three are the roster method, which is sometimes called the listing method. The second is set builder notation. So that's the set builder notation. And lastly, the Venn diagram. So these are the three methods of describing the sets, and I'm going to take them one after the other and explain. So we begin with the roster method. Now, with the roster method. With the roster method, sometimes called the listing method, with this method, elements of the set are being listed directly. So, to represent sets using the roster method, this is how you're going to go about it. So, let's say we have set A, 1, 2, 3, and 4. So, with this, we can see that the element of set A, we can say directly. So, these are the elements of set A, and that was how to represent sets using the roster method. I hope it is clear. Now let's go straight to the second one, the set builder notation. Now with the set builder notation, the elements of the set are described by the property that characterizes them. So to represent sets using a set builder notation, please take note of this. This is how you go about it. So let's say set A contains these elements, but you are not going to list the elements as I did for the roster method. With a set builder notation, the elements are being described by the property that characterizes them. So let's say set A is a set of all x such that x is an even number less than 10. So this is how to put sets using a set builder notation. This is just an example I've given. And this is how you are going to put your sets when you are using a set builder notation, or when a question asks you to put a set in a set builder notation form. So that is it. Now let's get straight into the third one, which is the Venn diagram. So I'll be talking more about the Venn diagram in my next video. So let me quickly explain how or the way to represent sets using the Venn diagram. So the Venn diagram is a visual representation of set problems, and it is normally using closed diagrams, normally circles, within a rectangle. That is the universal set. So with the Venn diagram, I'm not going to talk more about it now. In my next video, I will talk more about the Venn diagram. So for now, let's skip the Venn diagram and move on to the types of sets. Now the types of sets. So there are so many types of sets, but I'm going to take you through 8 of them. And these 8 are, the first I can talk about is the empty set. We have a finite set. We have the infinite set. We have the universal set. We have complement of a set. We have the subset. We have the proper subset. And lastly, the polar set. So these are the 8 I'm going to talk about. So let's begin with the empty set. So with the empty set, with the empty set, it is a set that contains no element. So as the name suggests, empty, it contains no element. And it is normally denoted by this sign here, or an opened and a closed curly bracket with no element. And this is an empty set. So let's move on to the second one, finite set. Please, I hope you are following. It is very simple. So let's move on to the finite set. So the finite set is a set that contains definite elements. So a set that contains definite elements. For example, set A. So as you can see, it contains a definite element. When you talk about definite element, the last number of the set is known. So we can see from this element here that 4 is the last element of set A. And that is a finite set. I hope it is clear. Now let's move on to the third one, which is the infinite set. So the infinite set is the opposite of the finite set. So with this one, it is a set that contains countless elements. So for example, set A contains 1, 2, 3. So as you can see, it goes on and on and on. Its last element is not known, and that is an infinite set. I hope you understand. Okay, so please let's move on to the fourth one, which is the universal set. So now a universal set. Universal set is a set that contains all the elements under consideration, and it is usually denoted by the capital letter U. So this is the universal set we're talking about. So universal set is denoted by this capital letter U here, and that is the universal set. Please, I'm going to talk more about all these in my next video when we are solving some practical questions. Now let's talk about the next one, which is the complement of a set, or complement of sets. So with the complement of a set, I'm going to explain with an example. So let's say we have set A and the universal set. So this is an example. You have the set A here and the universal set. So the universal set, as I said, is the element, it contains the elements, all the elements under consideration. So this is the universal set and this is the set A here. So with a complement of a set, a complement that is normally denoted as, so the set we are talking about here is A. So with a complement, this is how I'm going to go about it. So A complement. So this is how I'm going to go about it. So with the A complement, or a complement of a set, it is a set that, so let's say we have the set A here and the universal set. Complement of a set simply means the elements that are in the universal set but not in the set we are talking about here, which is A. So which element is in the universal set but cannot be found in the set A? So complement A, or A complement, is going to be 4 and 5. So we can see that 4 and 5 is not in A. We cannot see 4 and 5 in A. So complement of a set simply means the element that is, or the element that are in the universal set but cannot be found in the set here or the set A we are talking about here. And that is a complement of a set. Now let's move on to the subset. So now subset. So I'm going to explain the subset using two sets here. So A is a set, B is a set. So A is said to be a subset of B if the element of A can also be found in set B. So let's say we have A, B, and C. And B is A, B, C, D, E, and F. So these are the elements of A, these are the elements of B. So A is said to be a subset of B because A, B, and C can also be found in set B. And that makes A a subset of B. And it is usually denoted as this. So A is a subset of B. And the elements are A, B, and C. So A is a subset of B and the elements are A, B, and C. And that is a subset. Now let's go straight to the proper subset. Now the proper subset. So with the proper subset, I'm going to explain with an example. So let's say you have set A and set B here, and the elements are A, B, C, and D. And that of the B is A, B, C, D, E, and F. So these are the elements of A, elements of B. Proper subset simply means the element of A here should also be in B, but the elements, the total number of elements in each set shouldn't be the same. So A is a proper subset of B because the element of A can also be found in B, but the total number of elements here is not equal to the total number of elements in B, and that is a proper subset. So the question would be like, proper subset, is A a proper subset of B? And the answer is yes. A is a proper subset of B because the element of A can also be found in B, but it is not equal to B. And that is the proper subset. So the question again can be rephrased as, is B a proper subset of A? The answer is no, because A, B, C, D, E, F cannot be found in A, and that makes B not a proper subset of A. So that is a proper subset. I hope it is clear. Now let's move on to the power set. Now the power set. So the power set is simply talking about a possible subset you can draw from a given set. So with a power set, let's say we have set A containing 1, 2, 3. So 1, 2, 3 are the elements of the set. So what is the power set of A? So the power set of A simply means a possible subset you can derive from this set here. And the power set, it normally contains an empty set in the set itself. So let's first of all draw the subset from this set here. The subset is going to be an empty set 1, 2, 3, 1 and 2, 1 and 3, 2 and 3, 1, 2, and 3. So as you can see, we have an empty set here and a set itself. And these are the subsets of A. And to write this subset in a power set form, this is how I'm going to go about it. The power set is normally denoted as, so the P here stands for the power, and then the set we're talking about, the set under consideration. So P, the power set of A, you are going to list all these subsets. You are going to list all these subsets in a set form. So the power set of A is the list of the empty set 1, 2, 3, 1 and 2, 1 and 3, 2 and 3, 1, 2, and 3. And then you close your set. So this is a power set I'm talking about. So it contains a subset of a given set. So these are the possible subsets of set A. We have 8 subsets here, and this is the way to represent it in a power set form. So I believe you understand the power set now. Now let's move on to our next topic, finding subset in a given set. So our next topic here is finding subset in a given set. So to find a subset in a given set, please, there's a simple formula you can use. So let's say the number of subsets. So this is the formula I'm given. So the number of subsets is equal to 2 to the power n. And the n here represents the number of elements the set will contain. So for example, let's say A contains 1, 2, and 3. So from this example, we can see A contains only 3 elements. So the n here will be what? 3. So to find a subset of this set here, you replace n with 3 in the formula. So it's going to be 2 raised to the power 3, and that is 8. So this set here contains 8 subsets. And what are these 8 subsets? That is the empty set 1, 2, 3, 1 and 2, 1 and 3, 1, 2, and 3, and then 2 and 3. So these are the subsets of set A, and that is a simple way you can find a subset in a given set. Now we are on the operations of sets. There are 3 main operations of sets, and these 3 are the union of sets, intersection of sets, and the difference of sets. So I'm going to take them one after the other and explain. So we begin with the union of sets. So with the union of sets, it simply means bringing the elements of 2 sets together. So for example, let's say set A and set B. So set A contains A, B, and C. So these are the elements of set A, and B, C, D, and E. Union of set is saying that bring these 2 elements together to form the union of set. And the union of set is normally or usually represented as A union B. So to bring this element or this set together, this is how I'm going to go about it. So A union B is going to be A, B, C, D, and E. So I know we have the elements A, B, C, D, E as the union of these 2 sets. Now let's move on to the intersection of sets. Now the intersection of sets. So the intersection of sets, I'm going to explain this with an example. So let's say we have set A and set B. Set A contains A, B, and C, and set B contains C, D, and E. So intersection of set is saying the elements that can be found in A and at the same time can be found in B. And it is usually represented as A intersection B. And from these elements here, which element is common to both A and B? And of course, it's C. So A intersection B is equal to C. And that is the intersection of sets. I believe you are getting the concepts one after the other. Okay, now let's move on straight to difference of sets. So difference of sets. Now the difference of sets, please pardon me, I'm going to explain with an example. So let's say we have set A and set B again, and set A is 1, 2, 3, set B 3, 4, 5. So the difference of set is saying the element that is in A but not in B, and that is the difference of set I'm talking about. So the elements that are in A but cannot be found in B. And the difference of sets, to write the difference of set, this is how you are going to go about it. A minus B. So which elements are in A but not in B? So we can write A minus B as 1 and 2. Please, the answer is 1 and 2 because I'm saying the element that can be found in A but not in B, and it is 1 and 2. But let's say the question was find B minus A. That means the element that is in B but not in A, and the elements are going to be 4 and 5. So this is saying the element that is in A but not in B, the element that is in B but not in A, and these two are different. Now let's quickly move on to the properties of set operations. So we are now on the properties of set operations. These there are 3 main properties of set operations, and I'm going to talk about them. And the 3 properties are the commutative property, the associative property, and lastly the distributive property. Now let's take them one after the other and explain. So we begin with the commutative property. So the commutative property, it's talking about the order in which you combine sets doesn't affect the result. So using the operation of sets, the union and the intersection, let's see how the commutative property works. So let's first of all take the union. So union, and you are going to represent it as, so let's say you have 2 sets A, so it will be A union B. Commutative property is saying the result you get for A union B shouldn't be different from B union A. So for example, set A contains A, B, and C, and set B contains D, E, and F. So there is an example to prove the union using a commutative property. So let's see. A union B. So A union B, the union, as I explained earlier, is bringing the element together. So let's see. A, B, C, D, E, and F. So this result here, so A union B, and this is the result. So this result here should be equal to the result of the other side of the commutative property, that is the union. So let's say B union A. So this result should be equal to this. And of course, to combine B, set B, and set A, you are going to get the same as A union B. So A, B, C, D, E, and then F. And that is a commutative property using the operation union. Now let's talk about the other operation, which is intersection. So intersection. So for example, let's say A contains the element A and B, and B contains the element B and C. Intersection. So the commutative property, mathematically using the intersection, can be given as A intersection B. So it's saying that the results you get for this shouldn't be different from B intersection A. So A intersection B, let's find it from this example given. So we have A intersection B. So intersection simply means the element that is in A and at the same time in B. And the element is B. So A intersection B, we have B. So the other is saying the same. So B intersection A means the element that can be found in B and at the same time in A. And the commutative property is saying that the answer or the result you get for this first one shouldn't be different from the other. So B intersection A automatically is going to be B. And that is the commutative property. Now let's move on to the associative property. So now the associative property. So the associative property is saying that when you combine 3 or more sets, the way you interchange them doesn't affect the results. So let's use the operation of sets as I use for the commutative property. So let's say you have union. So mathematically, it can be represented or it can be given as, let's say we have 3 sets, A, B, and then C. So the associative property is saying that no matter how you interchange them, so let's say A union B union C, these results here, the results you get for this side should be equal to A union B union C. And that is the associative property when you use the operation union. So this side shouldn't be different from this side, I mean the results. So now let's take an example. So now let's say we have set A, B, and C. So set A contains 1 and 2, set B contains 3 and 4, set C contains 5 and 6. So let's see if the results we are going to get for this will be the same as this. So let's begin with the first one, A union B union C. So now let's get our element. So the element of A union into bracket B union C is going to be, so the first set we are talking about here is A. So you bring the element of A, that is going to be 1 and 2. So 1 and 2 union, what is the combination of B and C? So B and C is going to be 3, 4, 5, and 6. So now we have these 2 sets here. So we bring them together because of the operation here, which is union. So A union B union C will be equal to 1, 2, 3, 4, 5, and 6. So now there is a result for the first one here. So the associative property is saying that even though we've interchanged the signs and the operations here, even though we've interchanged it, the result for this will be the same as this. So let's check this out. Now we have A union B, or in one bracket, union C. So now let's see. What is the combination of A and then B? So we have 1, 2, 3, and 4. So that is the first one. So the first one, union the C, and the C is 5 and then 6. So now let's bring this element or this set together because of the operation sign union. Let's bring them together. So A union B union C is going to be 1, 2, 3, 4, 5, 6. And that proves what the associative property is saying. This side is, as you can see here, it's the same thing. The results didn't change. It's the same thing. So that is the associative property we are talking about using the operation union. So now let's check the other side. Now let's use the intersection. Now the intersection. So as I explained earlier for the union, same applies to the intersection. But in this case, the intersection is saying that, so let's say we have 3 different sets, A, B, and then C. So no matter how you interchange them, your result is going to be the same. So let's say you have A intersection B intersection C. So the result you get for this should be equal to A intersection B, or in one bracket, intersection C. So this is what we are talking about under the associative property. So now let's solve an example and let's prove whether this is true. So example, we have the set A, B, and C. So A will contain, let's say, A and B. Set B will contain A, B, and C. And set C will contain C and D. So now this is an example to prove the mathematically shown formula here. Now let's see. A intersection B intersection C. Will the result of this be the same as this? The result should be the same. That is what the associative property is saying. If the result differs, that means your work or your solution, you have to check your solution. Okay, so now let's prove it first. So let's see. A intersection. So you first of all so this is the set A. So we bring our set A, the element of set A is A and B. So A and B intersection, what is the combination? Sorry, in this case, intersection. So what or which element can be found in B and at the same time in C? And that is the element C. And that is the element C. So A intersection B intersection C. So now, we are talking about intersection here. So which element can be found here and at the same time here? There is no element. And that is going to give us an empty set. Or in this case, you can represent it as this. So it gives us an empty set. So let's prove the other side and see whether we will also get an empty set. So we have A intersection B in one bracket, intersection C. So now let's see. So which element can be found in A and at the same time in B? So that is the first one. So we have A and then B, right? Okay. So A and B intersection C. So now C here is C and D. Now this is how far we got into. So A and B, C and D. Which element can be found here and at the same time can be found in this set here? And the answer is none. So A intersection B intersection C is also going to be an empty set. And that proves what the associative property is saying about the intersection. So I believe you are getting the concept, and that is the associative property using the operation union and the intersection. Now let's move on to the last one, which is the distributive property. So now the distributive property. With the distributive property, it connects the operations of set. That is the two main operations of set. That is the union and the intersection. So it says, or it connects them, as I said earlier on, which one distributes over the other. So, as I did for associative and then the commutative, I'm going to do the same for the distributive. Let's prove the property using some examples. So let's say we have three sets A, B, and C. So with the distributive property, it normally works when three sets or more are given. So let's say we have sets A, B, and C. Now, the distributive property, as I said, it connects the union and the intersection. So we have, let's say mathematically, let me give you this. So we have A intersection B union C. So the result you get for this, should also be equal to, so in this case, this one here, the intersection is distributed over the union, as you can see. So if the intersection distributes over the union, it should be same as if the union distributes over the intersection. And that one is going to be A intersection B union A intersection C. So this one here is showing the union distributing over the intersection. Now let's prove this, and let's prove with an example. So we have set A, set B, and set C. So set A will contain 2, 3, 4, and 5. Set B will contain 1, 2, and 3. Set C will contain 5, 6, and 7. So this is just an example. Let's prove this distributive property here. So the first one, as I said, is the intersection distributing over the union, and this side, the union distributing over the intersection. Now let's prove the results. So the first one we are going to talk about is the intersection distributing over the union. And the first one, we are supposed to list the element of set A. And the element of set A are 2, 3, 4, and then 5. So intersection, the combination of B and then C. That's set B and then set C. So what would be the union of set B and set C? That would be 1, 2, 3, 5, 6, 7. So that is the union of set B and then C. Now, let's move on. So, at this point, the operation here is intersection. So, which elements can be found here and at the same time here? So now, the result of the intersection distributing over the union is going to be, so the element that can be found here and at the same time here, we can see 2, 3, and then 5. So, if the intersection distributes over the union, the result is going to be 2, 3, and 5. Now, let's check the other way when the union distributes over the intersection. So, that would be A intersection B union A intersection C. Okay, now let's prove this, and let's check whether the results we'll get for this will be the same as this. Okay, so A intersection B. So as we can see here, what will be A intersection B? So which element can be found in A and at the same time can be found in B? And the answer is 2 and 3, right? Okay. And now what is the intersection of A and then C? So the intersection of A and C, from this we can see the answer is 5. So now we bring this together because of the operation union here. So now A intersection B union A intersection C is going to be 2, 3, and then 5. And that is it. That proves what the distributive property is saying. It connects the union and the intersection. Which one distributes over the other? And that is it. So as you can see, when the intersection distributed over the union, we had 2, 3, and 5. And same for when the union distributed over the intersection, we also had 2, 3, and 5. And that brings us to the end of today's lesson on sets and operation on sets. Please remember, understanding these basic concepts is the foundation for solving more complex set problems, especially in your exams. So in our next video, I'm going to talk more about the Venn diagram. We're going to solve more practical questions. So for now, please revise your notes, try some practical questions, and get ready for the next lesson. Don't forget to like, comment, and subscribe to my channel for more Maths Mastery. And please ring the notification bell so that you won't miss the next video when it drops. Thank you. I'm Benjamin Nasu Kwame. Math is not difficult, it just needs mastery. Thank you.